Okay, so good morning, everyone. Let us continue with where we left last time. So we were doing gamma distribution, and we did not define gamma distribution, but we defined something called gamma function. Gamma function is a. Can you turn off the microphone? So I request you to turn off the microphone. Yeah. So as I said, gamma function is an extension of the factorial. Okay, and factorial function we know. Okay, so in this case we have defined gamma n to be n minus 1 factorial. Okay, it's like one less. Okay. And then what I said is like we can extend this factorial function by so-called gamma function here. Okay, so we know the values for the integer arguments, but what we are saying here now is like, can we extend this factorial function for real values? Okay, or for positive real values. Okay, so it's like a real values which are like positive. Okay, so. So to do that, and then if we see the curve, then somewhat we have to do something like this. It's like some kind of an interpolation. Okay, so here at 1, it's like 1. Okay, so like 1 minus 1 is 0 factorial, and then here it's like again 1 factorial, which is again 1, and then at 3 it will be like 2 factorial. So this way, like we have to find a interpolation and so on. Okay. So such that this interpolates very nicely in a continuous way. Okay, so if that is the case, then for any intermediate values, I will be able to find what is the value of the gamma function here. Okay, so this is the expression for obtaining a general or a analytic continuation of the factorial function, which is called gamma function. Okay, so and here alpha must be greater than 0. Okay, so and then we saw the properties. Like first one is not really properties, the definition of the gamma function itself, and second one is the property. Okay, so what this says is that this expression here is equal to gamma alpha divided by lambda to the alpha for lambda greater than 0. So lambda is the expression here. Okay, so somehow it relates this integral to the gamma function divided by lambda to the alpha. Okay, so this is something we may try to prove. And gamma alpha plus 1 is alpha gamma alpha. So this is the recursive thing that we need in the factorial function. Okay, so for integer values, we already know that due to recursion, it will behave like n minus 1. I mean n factorial. Okay, so the fourth one is an immediate consequence of this. For integer values, this is what we will get due to the recursion that the gamma function satisfies. And the fifth one is gamma half is square root of pi. Okay, so these are the properties. Like these are all like maths, right? So we need to like figure out from our calculus and all those things that we have studied to prove these integral properties. Okay, so it's nothing but like integral properties we are trying to prove here, right? So so properties of the gamma function. Let us do the. So the first one is. First property is just the definition, so nothing to do here. Okay, so this is the second property that we have to prove, and to prove this, like we may want to do a change of variable. Okay, so I have a space here and here. Okay, so we may want to do the change of variable, and what could be the good change of variable here? Because I see like you see somehow I have to relate somehow I got to relate the gamma function somehow. Okay, I mean what I'm trying to say is like somewhere there is some gamma function embedded here up to the scaling of lambda alpha, right? So it seems like if we do a change of variable, like in the gamma function we had, so gamma of alpha we had was 0 to infinity x to the alpha minus 1 and e to the minus x dx. Okay, so this is the gamma function that we know. Okay, so what we want is like, can we, and what is changing here is this lambda factor here. Okay, so looking at the right hand side, what we feel like is that this thing is something of the form gamma alpha, and then there is a scaling factor here. So it suggests that maybe we can go for some change of variable, like maybe like if we choose lambda x is y, this with this change of variable, we may get this resulting term in gamma, and then some scalar factor may come out. Okay, so that seems to be the case, because this is not going to disturb this term here. Okay, obviously it's going to disturb this term, but this term will be 1 over lambda times the new variable, right? So we can already see like what we can do next, right? So what we can do is like we can substitute lambda x is equal to, or we can substitute like lambda x is y, I guess that will work, or so let's see, okay, so, or the other way, right? Yeah, so or we may start with alpha and we introduce this lambda here. Okay, that's another approach. Like either way, like we can try. Okay, so another possibility is that we start from gamma alpha and we put a substitution of x by some lambda y, such that we see this guy here. Okay, so we have to like spit out this term. If we go via this way, then we start with gamma alpha, x, we introduced lambda here, so it would be lambda y, and then we have to change things here. So there are two ways to go. If I go by, let us say gamma alpha, what do I have? Okay, so in gamma alpha, let us say I do the change of variable. Okay, so do change of variable, let us say. Okay, I want to do the change of variable, which is x is equal to lambda y. Okay, so that I bring in this lambda thing here. Okay, so what happens to the limit here? For the limits, because we did the change of variable, so we have to see is whether the limits change now. So if x equal to 0, then y is also going to be 0. Okay, because lambda is positive. So x equals to 0 implies y is equal to 0, and x is equal to infinity. It also implies y is equal to infinity. Okay, because lambda is some fixed number. Okay, so to become infinity, y has to become infinity. Okay, so the limits don't change, so it's still 0 to infinity. Now with this change of variable, let us see if we can get the left hand term, which is this one, right? So so gamma alpha is 0 to infinity lambda y, okay, because this is lambda y, to the alpha minus 1, and e to the here, okay, e to the minus lambda y, okay, because x is lambda y, and then dx. So from here we have dx is lambda dy. Okay, so in place of dx we have lambda dy. Okay, and constants we will bring out. So what are the constants here? Lambda is a constant, so lambda alpha minus 1 is here, and then is one lambda here. So lambda to the alpha will come out, and then it's 0 to infinity, and then y to the alpha minus 1, e to the minus lambda y dy. Okay, since okay, so but what is this guy here, right? So what is this guy here? So this guy is, isn't it this exactly the left-hand side, right? It's just that the variable is y, right? But variables don't matter, right? In the integration, if the variable is same throughout, right? So this is our left-hand side, and this is our right-hand side. Okay. So this is exactly equal to lambda to the alpha times the left-hand side. Okay, left-hand term or left-hand side. Okay. So this implies, okay, so this implies y to the alpha minus 1. So this is the left-hand side. I'm just trying to write lambda y dy is gamma alpha divided by lambda to the alpha. Okay, so change back y to x. So change back y to x. Okay, and you get this thing in x. Okay, because changing the variable, because it's a variable, it's just a notation, right? So y can be changed back to x. This is not related to this x. Okay, I hope you understand all this. Okay, so this x is not this x. Okay, so it could be some arbitrary x again. Okay, okay, so change back and then we get the result. Okay, to get the result. Okay, so this was the property of second property, right? Okay. Okay, so now third and fourth property. Let us look at third and fourth property. So gamma alpha plus 1 is alpha gamma alpha, right? So gamma alpha, we can reuse what we have proved actually. So what we have proved in the previous one is, let us write down. Okay, so gamma alpha is lambda to the alpha and y to the alpha minus 1 e to the minus lambda dy. Okay, so this is 0 to infinity y to the alpha minus 1 e to the minus lambda y dy. Okay, and what we will do is like we will do integration by parts, because what we see is like this is a recursive thing, right? So what we believe is like recursively it should give us something, some term, right? Let us say recursively it should throw us some term in gamma itself again, right? So we want to find out, and that will that should happen if I just go ahead and do some integration by parts. Okay, and just see what comes out of that. Okay, if there is some recursion, then I will find out. Okay, so let's see. So I mean, can I relate alpha with some gamma alpha plus 1 hidden here? Okay, so that's the question here, right? So okay, so let us see. So this is lambda to the alpha, and then I will do integration by parts, right? So let us say this is the first function I choose, first function, and this is the second function. Okay, so the first function into integration of the second, right? So the first function is e to the minus lambda y, into integration of the second will be y alpha by alpha. Okay, so this need to be evaluated 0 to infinity. Minus of integral of differentiation of the first. So differentiation of the first is minus lambda e to the minus lambda y. Differentiation first into integration of the second, right? So integration of the second is y alpha by alpha. Okay, and yeah, that's it. So this is dy, and this goes from 0 to infinity. Okay, so this will be okay. So if we evaluate this, so in this case, if you see, if I put y to be infinity, then that term is 0, and then minus, and if I put y 0, then this term is 0. So overall, this term is going to be 0. So what we are left with is lambda to the alpha, and this is like plus lambda by alpha. So this is what we are left with here is lambda by alpha, and then this is integral 0 to infinity. So let me just write things in a in a clean way. So this is like y to the alpha is left, and e to the minus lambda y dy. Okay, so that's what is left, and we are supposed to do this. So lambda, one lambda goes out, so this is lambda alpha plus 1 by alpha, and then this is 0 to infinity y to the alpha and e to the minus lambda y dy, right? Okay, so how do we recognize this, right? How do we recognize this term, right? Let us write down the gamma alpha. What was actually the gamma alpha? 0 to infinity, x to the alpha minus 1 and e to the minus x dx. So this was the gamma function, right? Okay, so this is the gamma function, and we want to see whether like we have like something in hand already. And remember that this is like in terms of lambda y, right? So it seems like we have done some property like in the previous case. So in the previous result, what we have, the previously. So if we flash back our memory, so this was 0 to infinity y to the alpha minus 1. Okay, so previously it's like here y to the alpha minus 1 e to the minus lambda y dy was this, right? Y to the alpha minus 1 e to the minus lambda y dy was gamma alpha by lambda to the alpha, right? So this was the property that we had. So property 2, right? So if we look here, right? So what is the thing that is changing here? Like alpha is the term. Like somehow I see gamma alpha plus 1 type term here, right? So using this, what do we have? So let us keep these guys here, alpha plus 1 by alpha. And this guy, if you look up from here, this should be equal to alpha plus 1 thing, right? So alpha plus 1 by lambda alpha plus 1, right? So this is like gamma alpha plus 1 by lambda alpha plus 1. Okay, so this is like lambda alpha plus 1. Okay, so this alpha plus 1, this alpha plus 1 gets cancelled. So we have derived gamma alpha up to here, right? So this implies gamma alpha plus 1 is alpha goes there. Okay, so gamma alpha. Okay, so this is the proof of the recursive nature of the gamma function. And the fourth property is trivial because I used alpha to be very generic real number. So obviously like it should hold for integer values. So okay, so property 4 is obvious. Okay, set alpha to be n, set alpha to be n and apply recursively, apply 3 recursively. Okay, so we know this, right? So fourth is just a special case of this. Okay, so this is the thing. The fifth property, the last property of gamma function is gamma half is square root of pi, right? So in other words, what does this mean? Like half minus 1 factorial is square root of pi. Okay, if we can still take liberty of using the notation factorial. So minus half factorial is square root of pi. Okay, so this is the what we are interested in proving. Okay, so how do we prove this, right? So what are the things we have in hand? Okay, so gamma, I mean, if we write down the gamma again, like it's good to write again and again so that you memorize. 0 to infinity x to the alpha minus 1 e to the minus x. Okay, so what this is saying is ultimately gamma half, gamma half. So gamma half, which is 0 to infinity. Okay, so in place of alpha we have to put half, right? So x to the minus half. Okay, only in place of alpha. Okay, so e to the minus x dx. So this integral evaluates to pi. Okay, so this is now the integral calculus. Okay, so many things in probability actually boils down to just calculus actually. Okay, in the continuous random variable case, calculus and combinatorics. Okay, so this is what we have to prove. Okay, and so if you are good in calculus, you will prove it anyway. Okay, if you are good in integral calculus, you will prove it. But to recall, in case you guys have forgotten, then I will prove this right now. Okay, so how should I go about proving this, right? So some kind of substitution method or something like that. Okay, so what I may need is so-called polar coordinates to prove this, and what I will also need additionally is something that I have not proved for the normal. So in the normal distribution, remember we defined the PDF to be 1 by square root of 2 pi e to the minus x square by 2. Okay, so that was like the PDF of the normal distribution, a standard normal, right? So that's how it was defined, and I did not prove that the integral of this PDF will be 1, right? So actually, it's some of the terms here will use that fact. Okay, so so we will cover that also while we are doing this. Okay, so let us see. So the first step. So there will be like 3 steps in the proof of this. So first, we will show the fact from the calculus that dx dy is r dr d theta. Like how many of you remember that dx dy is r dr d theta? Like do you know the proof of this or just the intuitive thing? Second, we saw that the constant in the normal distribution is 1 by square root of pi 2 pi. This may sound like coming out of nowhere right now, but actually it's needed in the proof of this result of the gamma function. And finally, we will use 1 and 2 to show the final result, right? So let us see quickly what was the thing when we move from dx dy to polar coordinates. Okay, so why the area is like this, right? So I mean it's so what we are saying here is if I move from xy, okay, so dx and dy area, okay, so dx dy area could be like a rectangular, right? So dx and dy is here, and then if I move to some polar coordinates, then the corresponding area is like r dr d theta. Okay, so that's the corresponding coordinates, and so the change of for the polar coordinates we do the substitution usually x is equal to r cos theta and y is equal to r sin theta. So we can do this quickly. So del x by del r dr plus del x by del theta d theta, and dy is del y by del r dr plus del y by del theta d theta. Okay, that's the differential of this. You recall calculus, and so what is happening here is that this rectangular element is now being transformed to a area in the polar coordinate, but in the polar coordinate where the area is defined by the vectors now. Okay, so the vectors, so vectors with the coordinates given by, I mean, these are the coordinates, and we went to the dr and d theta space, right? So dx now is written in terms of dr and d theta, and similarly dy is written in terms of dr and d theta. So these are the elementary vectors. I mean, you can forget about this small band because it's small anyway. So now the question is like, what is the elementary area of this spanned by these vectors r dr and r d theta? Okay, so what is the area spanned by the vector? So area spanned by, or the parallelogram formed by the vectors r plus dr and r d theta. Okay, so so in this case, like what we will do is like these are the vectors, the representation of dx and dy in the new, like I use like like linear algebra, right? So I can write dx dy in terms of some other vector coordinates. So these are the coordinates, okay? And then we have to do the cross product of this to find the area, okay? So we have to find the cross product. So cross product to find the area, to find area in polar coordinates, okay? So if we do the cross product of this, so if we write this down, then in our case, this will be like cos theta dr minus r sine theta d theta. And in this case will be sine theta dr plus r cos theta d theta, right? So you can do these partial derivatives and so on. And then the cross product will be like the determinant, right? In this case. So this will be so dx dy area. So you see this as an area. You don't multiply directly like the usual multiplication you do, right? So this is like this is like the cross product, right? So in this case it will be this. So this will be like r dr d theta after simplification. Okay, so this is like the after cross product. Okay, so we know like this is the thing that we know. Okay, so now let us go ahead and now do the proof that the constant in the normal distribution. Okay, so the constant in the normal distribution is 1 by square root of 1 by square root of 2 pi. Okay, so how do we prove this? The constant is square root of. So we will use something called polar coordinates that we, and this will lead us into a little bit simpler case, and which is easier to integrate. Okay, you may be able to solve this in other way. Do this. Okay, so the normal distribution, right? So normal distribution, recall if x is normal 0, 1, then this implies fx x. Okay, so this was 1 by square root of 2 pi, right? And like minus infinity. Yeah, so this was e to the minus x square by 2 dx. Okay, so if I integrate this over over all the domain, it should be square root of 2 pi. Okay, so since fx is PDF, f, this implies minus infinity to infinity e to the minus x square by 2 dx must be 1 by square root of 2 pi must be equal to 1. So this implies that the integral minus infinity to infinity e to the minus x square by 2 dx must be equal to square root of 2 pi. Okay, so that's what like we are trying to prove here, right? So this is what I'm trying to prove when I say this. Okay, so we will show that. So let us say this integral is I. Okay, so we will show that I square is 2 pi. That's what we will prove. Okay, and then I will be like square root of 2 pi. Okay, so if I square is what then, right? So this is minus infinity to infinity e to the minus x square by 2 dx, and then we have minus infinity to infinity. It's just the square. So this is again, but I can use some other variable also. So minus y square by 2 dy. Okay, it doesn't change the I because the variable I can change. So this I can combine, and this becomes a double integral. So minus infinity to infinity and e to the minus and x square plus y square by 2. Okay, so this is 2 dx dy, and now we switch to polar coordinates. Okay, switch to polar coordinates. So if we switch to polar coordinates, So that is x is equal to r cos theta and y is equal to r sin theta. So this implies dx dy that we just proved is r dr d theta. Okay, so this implies I squared is so with the change of this. So in this new variables, after this change of variable, what we find is like theta will go from 0 to infinity. Theta will go from 0 to 2 pi because we have to turn full 360 degree, and r will go from 0 to infinity, right? The radius will go from 0 to infinity. So this will be our 0 to 2 pi. And e to the x square plus y square is like r square. Okay, so this is like minus r square by 2. Okay, and dx dy is r dr and d theta. So this is equal to actually here there is a dependence only on r. Okay, so theta thing can come out. Okay, so what we can write, I can write one more step. So this is like e to the minus r square by 2 and r dr, and the remaining integral is 0 to 2 pi, and just d theta is there. So this will turn out to be the integral of this will be like theta and then 0 to 2 pi. So this will be like 2 pi. So this thing will be 2 pi, and then this will be 0 to infinity r e to the minus r square by 2 dr. Okay, and this will be 2 pi and minus e to the. So if you do any you can do a change of variables. So you can do r square is some u, and then so the r dr will be now converted to du with some 2 factor and so on. So after doing all this, what I get is minus r square by 2. Okay, 0 to infinity, and that will be like 2 pi. Okay, so this implies like so this implies I square is 2 pi, and which implies I is square root of 2 pi. Okay, so this is what we were like supposed to prove in this case. Okay, so this proves that the constant of integration must be 1 by 2 pi in the standard normal. Okay, so now the next question is like gamma of half. So gamma of half must be square root of pi. Okay, so let us see what is like gamma of half. So if I write gamma of half, so this is 0 to infinity x to the minus half and e to the minus x dx. Okay, so let us say this is some I, and yeah, so I want to like change this into the form where you see like it may be like related to the standard normal. Okay, by doing some good substitutions. Let us try. So let x is equal to u square. This implies dx is equal to 2u du. Okay, so then let us say what is the integral I want. Let us say, so this is 0 to infinity. X is u squared, right? So this is like u squared and minus half, and ex is u squared. Okay, so times e minus u squared times 2 u du. Okay, so dx is like 2 u du. So this is yeah, so this is like how much? Like u cancels, right? Because u 2 cancels, so u minus 1 and u 1, so that gets cancelled. So it's like 2 of integral 0 to infinity e to the minus u square du. And how is this related to how is this related to the Gaussian density, right? So how is this related to the Gaussian density? Like for the Gaussian density that we have proved, it looks like this, right? So e to the minus x square by 2 dx is square root of 2 pi. So this is like x square by 2, right? And what we want here is just like x square, right? So what this will come out to be, right? So like what is the way that we can put this in this form, right? So you can already see what to do here. Like I can do a substitution such that it goes to this form. Okay. So for instance, I can do u to be let us say y by square root of 2. Okay. So y by square root of 2. So if I do that, then I will get this in this form. Okay, so let us do that. And this is a symmetric one. So 2 of this I can change back to minus infinity to infinity. I mean, this is even, right? So I can get up to here, right? And change of variable I want to do because I want to move this into Gaussian, because for Gaussian I know the formula, right? So change. So these are the things one has to do, right? So u to, let us say, y by square root of 2. This is the change of variable we do. So du is dy by square root of 2, right? And infinity, the limits won't change with y. So this implies I1 is minus infinity to infinity still, and e to the minus u square, right? So minus u square will be minus y square by 2. And du will be dy by square root of 2. So du is dy by square root of 2. So this is 1 by square root of 2 and minus infinity to infinity e to the minus y square by 2. Now e to the minus y square by 2 dy. Okay, so there is always like dy here. So e to the minus x square by 2 dx, or it's the same thing as saying e to the minus y square by 2 dy is square root of 2 pi, right? So this guy is like square root of 2 pi, right? So this is equal to square root of 2 pi. Okay, so this is equal to equal to square root of 2 pi divided by square root of 2, which is square root of pi. Okay, so this is what we were supposed to prove. Okay, so we started from here and we ended up here. Okay, so this is the proof of the last property of the gamma distribution. Okay, so gamma distribution can be okay, so I have one more like problem here. Okay, let us do this quickly. This is like, so far we are doing gamma function, right? I've not defined gamma distribution. So gamma 7 by 2, let us say someone asks you to compute gamma 7 over 2. What do you do? Okay, so in this case, what do I do? Gamma half, no, gamma 7 by 2 I'm supposed to calculate, right? So can you use the recursive property, right? So we can use the recursive property. This is 5 by 2 gamma 5 by 2. This is equal to 5 by 2 times 3 by 2 gamma 3 by 2. Remember, gamma alpha plus 1 is alpha gamma alpha, right? So these are the properties we are using. And this is 5 by 2, 3 by 2, 1 by 2, gamma half. Gamma half we just computed, right? So this is like square root of pi, right? So the whole thing is like 5 by 2, 3 by 2, 1 by 2, and square root of pi. Okay. And find the value of the integral. So this is the integral we have to do. So this is the first part. So let's say this is the first, this is the second part. So in the second part, what we can do is like, for this integral, we can like recall because this is of the form like lambda and then x to the alpha. Okay, so this seems something like we have seen before, lambda x dx, right? So it seems like we can choose alpha to be like, so it was alpha minus 1, right? So alpha to be 7 and lambda to be 5. Okay, so it seems similar. And then we had a property that relates this to to gamma alpha. So what was that property? So property 2, if we recall, property 2 was 0 to infinity x to the alpha minus 1 e to the minus lambda x dx, and this was gamma alpha by lambda to the alpha, lambda greater than 0. Okay, so this was the property 2, right? And this seems to be useful now because this integral we have identified like this, and then we use this after that, right? So choose alpha is equal to 7 and lambda is 5. Okay, so with that we have exactly this form, and this will give us this. Okay, so this will be this will implies I equals gamma 7 by lambda to the alpha, right? So this is like 5 to the 7. So 5 to the 7. Okay, so gamma 7 is an integer, right? 7. So this is like 6 factorial. So gamma n is n minus 1 factorial. So 5 to the 7. So these were the like solved example of gamma. Okay, so gamma distribution is uses the gamma function. Okay, that's why we had to spend some time on that. So a continuous random variable x is said to have a gamma distribution with parameter alpha greater than 0, lambda greater than 0, and it's written like x this tilde and then gamma alpha and lambda if its PDF is given by this. Okay, so this is the PDF of a gamma distribution. Okay, so this may look a little bit complicated, but this is how the PDF is. And if we set alpha equals to 1, you will immediately realize that if you set alpha equals to 1, because this will be 1 factorial here, and you will be left with just lambda e to the minus lambda x. Now you recall what is this, right? Recall what was this? So this was the familiar exponential that we did, right? The continuous we have done uniform, exponential, standard normal, and then we are doing gamma, right? So we immediately notice that is 1 and you keep it, then it's nothing but the exponential function, right? So I guess that will be all for today. So we will see some examples of gamma distribution in real life where we can use this. Okay, so we will do some problems on this. And this will be more or less the end of the continuous random variable. And in the next class, we will do multiple random variables. So we will start with 2 random variables. OK, and we will see things like correlations, covariance, and all these things. And then we go to more than 2 random variables, functions of multiple random variables. Then we will prove some results like the main result, if you remember, it was central limit theorem. So that's a very famous result. So we will prove that. Law of large numbers we will prove, and many bounds we will prove. So Markov inequality and so on. And we will also touch maybe some random process Markov processes and so on, which are used a lot. Okay. I think you're following because most of this is calculus, and if your calculus is strong, I think there is no need to worry so much. Basically, you have to recall your integration. Okay, differentiation is not that much here, but integration is needed a lot. Okay, I think with this I will stop, and yeah, have a nice day. And if you have doubts that you could not ask, then you ask those in tutorial. If you still have doubts, then you ask in the Moodle forum. But do ask your doubts. Okay. And obviously you can ask doubts in class by asking in microphone. Okay, so I think I will stop with this. Okay, so thanks and have a nice day. Bye.